So last time we started talking about our applications, and that's where we're going to be for the next couple of weeks, is applications. And we're going to be talking about a lot of different things we can do with integration. And we talked about volume. And how do we find volume? Well, the idea is we take slices, and we look at our thin slices. And if we look at a thin slice, it's basically just like you take a little bit of an area with some thickness. Well, area times height, that's the volume of that thin slice, and you added it up. And we talked about a special case, which is volume revolution, where we spin something. And we said, okay, then in that case, our little slices might look like circles, or maybe they'll look like washers if there's a hole in the middle. And that's possible. But there's a different way that things could go. So that's today. So we're still going to talk about volumes of revolution today, but now in a slightly different approach. So what are we doing? Well, we're going to start with this region here, and we're going to spin, and we're going to spin it around this axis. So I'll put a little arrow here to help us see how we spin. And as we spin, we form a shape. Now, so far, nothing is different. Now, here's the different idea, which is how do we break things up? Because the whole idea of integration is break things up into small parts, each of which is relatively easy to understand. But how you break things up can vary. And sometimes you have flexibility in that there's multiple right ways to do it. So what we're going to do is we're going to think about breaking into small pieces. So you see here, there's this little tiny sliver that's been shaded. We're going to think of that as that's our small part. So let's focus on that little small part as we spin it around. Well, what will happen? It'll spin around, it'll come over to this side, and we'll get something that looks, something like that. So that's what we get when we spin it around. And so our shape is different. It's no longer just like a circle with a little bit of thickness. It's sort of like a can, the surface of a can. Now we call these shells. So what we're going to talk about, this is sometimes called the shell method. So what are we doing? Well, if we want to understand our volume, we have to understand our little piece. So we start with our shell. So here's our shell. And what are we going to do is we're going to pull out our scissors and start cutting. Okay? So we cut it. So probably can't see it, but it's now cut. And we just grab the edges and lay it flat. And now, so we've taken this cylinder, cut it and laid it flat. Now we have a nice thin box. Well, let's figure out what's going on here. There's a couple of things. Here, we can think of this as the height. Well, downstairs, that'll translate into a nice piece. So there's our height. Now, in terms of the picture, if we come back here, what does that correspond to? Well, the height is this. There's our height. In other words, it's how far up we went, up and down. Now, there's another part. Well, we'll do the easy one. This part right here. I'll think of this as our thickness. How thick is our shell? So that translates, we'll put it over here. Here's our thickness. Well, where is it in our picture? Well, the answer is, we've already marked it. It's this part right here. That's our thickness. Okay, so the last thing. Well, the last part, we'll call this our circumference. All right? How far we went around. So up here, that's all the way around. That's our circumference. Now, where is it in terms of the picture? Well, it's just all the way around. Now, we got to figure out how do we translate these different values. Well, some parts are pretty easy. The thickness, that's our small change in x, delta x, which becomes our dx. The height that's how high the function is. So we call it f of x. So the height becomes f of x. How about the circumference? Well, where you spin. And so what we're forming is a circle. So the circumference of a circle is 2 pi times the radius. So this becomes 2 pi radius. This is our circumference, this piece. So what is r of x? Well, r of x, if you come to this picture, we're really populating it. So r of x is the distance between these two pieces. It's from where you spin around to where your slice is. That is what r of x is. So it varies with x. So we have that one piece is 2 pi times r of x times f of x times delta of x. And now we say, all right, let's play our integration card. Integration card says, all right, if you know one piece, add them all together. And that gives you a total. And the way we add is we use the integral. So there we go. There's our total volume. Volume is 2 pi r of x, f of x, dx. But again, I don't want you to think about, let me memorize this formula, 2 pi r of x, f of x, dx. It's better to remember, okay, there's the radius to where we spin around. There's the height, there's the thickness, the 2 pi because we're doing a circumference. And then we add all of it up. All right, good. Well, that's the theory. Now the rest of today is practice. So any questions about the theory? Okay, well that was quick. All right. Oh, there is a question, yes.
Do you calculate the radius from the inner wall or the middle of the section?
Well, you don't have to worry about the intervals because the intervals are going smaller and smaller and smaller. So essentially, the intervals you should think of as having zero width in the limit. Of course, that's in the limit. So you don't have to worry about where the radius is. So it's really just, when we really do this in practice, we don't draw a box with any thickness. We say, okay, here's my box. It's no thickness at all. And then the radius would be from this point all the way to where you spin around. You don't have to spin around the axis, by the way. You can spin around any line you want. So that's why you want to remember radius and not just r of x. Yes, another question.
If you were to increase the thickness in this example where we see sort of curvature,
Right.
would that be possible to?
So if you increase thickness, the thing is that we don't want to increase thickness, we want to decrease thickness. Now you're going to get error. So anytime we apply integration, we think of it as, well, an approximation would have this kind of shape, where we have some mild thickness to start with, but we can do better and let our thickness go down. Now if you were doing an approximation to things and said, well, I have to find a volume of revolution, and I'm going to do it the old-fashioned way, then sure, you could let your thickness go up, but usually your error goes up. Because certainly it's true that if you start with a shell like this and you try to lay it flat, it's actually not so easy. If you have, the thicker it is, the harder it is to lay it flat, you're going to get a little bit of deformation. But the deformation goes to zero in the limit. So there's sort of a little bit hidden here when we say you lay it flat. Well, it's not quite that. But the details get swept under the rug because, well, as you take the limit, things get nice. Limits are actually your friends. I know some people are like, I'm done with limits. I hung out with them last semester and never again. But no, they're good. They're good. And considering it's Valentine's Day coming up soon, it's nice to write a little note saying, you know, I know we had some rough times together, but I appreciate all we went through. So, all right. Well, let us try a problem. So here we go. And we'll start with a nice big problem. Rotate the region bounded by 0 less than or equal to x less than infinity and 0 less than or equal to y less than or equal to e to the minus x squared around the y-axis and find the resulting volume. So, well, it's hard to draw the whole picture, but e to the minus x squared goes down as you head off to infinity. So there's the curve, and I'm only starting at 0. And it says to spin it around the y-axis. So we're spinning in that way. And what do we get? Well, what we'll get is on the other side, it'll have its sort of mirror image going down, but of course this is really spun around. So you can imagine, of course, it takes a while to spin it because there's infinitely long tail there. So there's our shape. There's our shape. So what do we do? Probably we should use our formula. All right. So let's recall volume, integral a to b. There's a 2 pi. And then I'll write there's a radius to where we're spinning around. Then there's a height. And then there's a little thickness. So that's our generic formula. And we just sort of start filling in the holes. So some of these, okay, so here's my little slice that I'm going to spin. And here's where I'm spinning around. What is the thickness? Dx. What's the height? Yeah, it's the distance between the two curves. There's the e to the negative x squared on top, 0 on the bottom, so the height, the difference between them, e to the negative x squared. The radius, how far between where I spin and where I'm currently at? So I think of where I'm currently at as being at x. So what's my radius? It's x. All right, and what are the bounds? 0 to infinity, which we can see because it says we're going from 0 to infinity. All right, so now we have our integral. So let's see. Let's just rewrite it a little bit cleaner. 0 to infinity, 2 pi x, e to the minus x squared dx. Now, if we were going to do this integral, what would we do next? Substitution. Yeah, you might be like, ooh, integration by parts. But remember, always check for an easy thing before you do a slightly less easy thing. So, substitution, what's the right substitution to make here? Minus x squared is a good substitution, or even just x squared, because you see that there's a function inside of a function. So when you see function and function, you're like, okay, that inside function, that could be a good candidate to make a substitution. So negative x squared, then du would be minus 2x dx. Well, I actually do have a 2x dx, so that's good. I'll just move the minus across. I'll put minus du as 2x dx. So we carry out that substitution. What will we get? Well, the pi is going to become pi. 2x dx will become a minus du. E to the minus x squared becomes e to the u. And where do we integrate from? Well, 0, that's my x bound, will become 0, because I'm going to square it. Infinity, where does that become? Or what does that become? Negative infinity. Now, of course, you can't just say, well, negative infinity squared. When we talk about infinity, we really say, what happens as things get big? So what happens to negative x squared as things get big? Well, it gets a big negative number, so it goes to negative infinity. All right, well, that's an integral that we can do. What's the integral of negative pi e to the u? Negative pi e to the u. That's why we like e to the u. I was talking to differential equations coordinator the other day. He says, yeah, that's sort of the big story of differential equations, is that we love e to the x, because it's so easy to integrate. So everything becomes e to the x. Now I spoiled differential equations for you. Well, yeah, you're going to love differential equations. Lots of e to the x. Okay, and now we're evaluating from 0 to minus infinity. Now, you might say, am I allowed to do that? Shouldn't I switch? And the answer is, you're allowed. It's okay. It's just a convention. There's nothing that says you can't. When we plug in minus infinity, which really means as we go to minus infinity, what happens to our e to the u term? It goes to 0. Then we're going to subtract. When we plug in 0, what happens to e to the u? Goes to 1, so we end up with the pi there. So 0 minus minus pi means this answer is pi. All right. So really, on these types of problems, mostly it's about the setup. The integrals usually aren't so bad. No big surprises. Now, we have talked about two different techniques. We've talked about the washer method. We've talked about the shell method. And you might say, well, when do we use which technique? And here's the simple answer. You can use either. So pick which one is easier. Now, how do you know which one is easier? It comes down to asking the question, how do I want to take my little slices? So, if I have a region, here's my region, I can think of slicing either horizontally or vertically. So in other words, I'm dividing up my region. I can do it in two different ways. Now, let's think about what would happen. Suppose we spin around the y-axis. If we were to slice vertically, as shown here, and we spin around the y-axis, the way to figure out what happens is just follow that slice. So as I say, if I spin this around, what's going to happen is I'm going to form that shape. So spinning vertical slices around the y-axis produces a shell. Okay, so how do I translate that? Well, this kind of slicing, this says that really we're having dx as little changes in x, because very small, thin changes. So this is our category. So we are in the vertical slice. So when you're doing vertical slicing, you're really integrating with respect to x. And so if we're rotating around a line, so here, x equals 0, that's the y-axis, that's going to produce a shell. So you can look at the picture will guide you. On the other hand, if you wanted to do horizontal slicing, well, that means that you're really doing dy, because you're just slicing up and little tiny changes in y. So that's in this line here. So you notice there's the dy. So this is the horizontal slice. And again, let the picture guide you. If I spin it, then what's the shape? What do you see? Yeah, I see a disc or a washer. So if you spin it around x equals 0 or x equals any number, you get a washer. But of course, that's if we spin it around, say, the y-axis. We don't have to. We could spin it in a different way. We could spin it here around the x-axis, which is y equals something. Now, suppose you were to spin this. What would you see if you spun that? See a washer. So if you spin it around y equals 0, integrating with respect to x, you get a washer. And if you take this piece and you spin it around, what do you form? You form a shell. So if you're not sure what method to do, draw a picture and just ask, what's happening to my little slice? That'll tell you which method you're in. All right. So, why do we want that? Well, sometimes one method is easier than the other. Let's try this. So let's use both methods. We're going to find the volume formed by rotating the region where x goes from 0 to 4 and y goes from 0 up to square root of x. So let's draw that. So let's see. X goes from 0 to 4, so there's 4. Then 0 less than or equal to y less than or equal to square root of x. So here, that's square root of x. And my picture's not the best. Where's this y value up here? Square root of 4. It's 2. So our region that we're going to spin is this region. All right. So that's what we're spinning. And it says using both methods. Okay, that means shell and washer. So, and we should mark that we are spinning that way, around the y-axis. All right, which one do you want to do first, shell or washer? Washer. The easy one. What? Okay, well, yeah. Maybe let's ask a different way. Do you want to first do a nice vertical slice, or do you want to do a horizontal slice? Which way should we do first? Horizontal, so here? All right, so let's do our little horizontal slicing. All right, so that says we're focusing on here. We spin this around. What's our shape? It's washer. So this is going to be a washer method. So a washer method, let's remind ourselves, it says A to B, pi, then there's a big radius squared, sometimes we call it the outer radius, and then there's an inner radius. And then we do it d something. Well, I'll call it the thickness. That's where our d comes from. All right, let's just go through. The thickness, what will it be here? dx or dy?
Yeah.
Or is it dy? So think about, this is our slice, right? So what has a small change? That's your d part. D, is it small change in y or is it small change in x? Yeah, it's a small change in y. It's just barely moved up and down in the y direction. So our thickness is dy. All right. What does pi become? Yeah, get some low-hanging fruit. Good. Now, let's talk about our bounds. This is a integral with respect to y. I know it's integral with respect to y because it says y right there. So that says my bounds need to be y bounds. So where does y go between? 0 to 2. Okay, so we're making good progress. So next, we have the radii. So let's start with the outer radius. So the way you find the outer radius is you start from where you're spinning, which is the axis, and you go to the farthest point away, which is over here. How far is that distance? 4. And notice it's always 4. So that becomes 4, and I forgot the square. Now, the inner radius, you start from where you're spinning, and you go to your curve. Now notice that's actually changing. At the top, it's 4, but at the bottom, it's 0. So what do? Well, we need to figure out where is this x value in terms of y. So we need to rewrite y equals square root of x. What does that become as x equals? X equals y squared. So what's the distance? From where we spin to this curve. It's y squared. Because there's x equals y squared, there's x equals 0. You subtract, that's how far apart they are. So this becomes integral 0 to 2 pi 16 minus y to the 4th power. Well, that's not a hard integral. The integral of 16 with respect to y. (16y). Integral of y to the 4th with respect to y. 1/5 y to the 5th. Evaluate from 0 to 2. Okay. 16 times 2? 32. 2 to the 5th is 32. So this becomes 32 minus 32 over 5. And you could do things like, for example, if you factor the 32 out, 32 pi, you get 1 minus a 5th. 1 minus a 5th, also known as 4/5. 4 times 32. Where's my electrical engineers at? 128. Now you might say, why is he picking on the electrical engineers? Well, because they like powers of 2. All right. So 32 times 4, 128. All right. So that's the answer if we use the horizontal slice. Now, we have to do it the other way. So we're going to do our little vertical slice. Okay, so that's this part down here. We spin it. What shape do we form? It's a shell. So, the formula for shell, integral a to b, 2 to pi, 2 times pi. Why do I want to raise everything to power? And then it's the radius, height, thickness. Okay, let's start with thickness. What is that going to be? dx. Because now our thickness is how much we're changing. It's this piece over here. It's a very thin slice with respect to x. Now we know it's integral with respect to x, so we can figure out the bounds. Where do we go from? 0 to 4. Because that's where the x goes between 0 and 4. The 2 pi becomes 2 pi. What's the radius? Well, the radius is from where you're spinning, when we spin around the y-axis, to our slice. So this is our radius, and we think of it are taking our slice at x. So how far is it from 0 over to x? X. Yeah. And oftentimes if you're spinning around an axis, you'll see something simple like x or y. What's the height? So the height is this length. Square root of x. All right, so there's our integral. We can clean that up. That's integral 0 to 4. And that's 2 pi x to the power 3/2. Well, that's the integral we can do. What's the integral of x to the 3/2? So you add 1 to the exponent, 5/2, multiply by the reciprocal, 2/5. 0 to 4. Now, that's 4/5 pi. Let's talk about these numbers. 0 to the 5/2, that's pretty easy. That's 0. 4 to the 5/2. Well, 4 to the 5th is, of course, 1,024. Good. And the square root of 1,024 is, of course, 32. Yeah, right? Now, if you're not comfortable with that, do it the other way. Because you can choose which order to take either the square root or the 5th power. Square root of 4 is 2. Okay, you agree with that one. And then 2 to the 5th. Just start working through the powers. 2, 4, 8, 16, 32. So that's going to be 32. So when we plug in, we'll get 4/5 times pi times 32, which becomes 128 pi over 5. Now, hopefully, you'll notice something about these two numbers. They're the same. Should that surprise us? No, it shouldn't surprise us. It should shock us if they were different. Now, why should they be the same? Because we're doing the same thing. We're computing volume. We're just doing it in two different ways. But we're computing the same thing. So we should end up with the same answer. So that's good. Good. It's consistent. We like it when everything matches up. All right. Find the integral, 2 pi times the integral from 0 to 1 of x, arctangent of x dx, without using integration by parts. Now see, we know how to do this, doing integration by parts. But now it says, no. No integration by parts will be harmed in the solving of this problem. So we want to find the answer without it. Now, at first, it seems like we can't do it. But here's the thing, is if you think of an integral as just an integral, then you're not using the full power of integration. What we can do is we can say this integral can be interpreted in some way. So let's think about how we can interpret this integral. So, how can we interpret? Can we see this as relating to anything that we've seen in the recent past? Shell method, right? It looks like shell method. What's sort of the clue that this could be a shell method? Well, there's a big one when you put the 2 pi. When you see 2 pi, that's a pretty big clue. Also when you see x, because oftentimes when you see a radius, it's something really simple like that. So it says, hey, maybe this is a shell method. So let's think about what shell method this is. We might say to ourselves, well, there's a couple things that are going on. We know it's integral with respect to x, and it goes from 0 to 1. So it says, all right, we're going to have x go from 0 up to 1. If we think about this x as being our radius, it actually tells us that what's happening here is that we're going to spin this way, because we really have it as x minus 0. So we think of x as our x is the location of our slice, and that's how far away from where we're spinning. So that says you're spinning back at the axis. Now, what does this arctangent of x correspond to? Well, this is corresponding to our height. So if this x is our radius, this arctangent of x is our height. So we have the curve arctangent of x. What a beautiful looking curve. Okay, so here what we're doing is we're slicing up arctangent of x from 0 up to 1. So let's say that here's 1. And then we're taking these shells and we're spinning it. So our shape is some sort of something like that. Okay. So this is what we're after. Or rather, you could say this integral I can interpret as a volume, where I'm spinning this region, and let's shade this region in. We're going to spin this region here about the y-axis. All right, so now we have an interpretation. It's not just that this is some arbitrary integral, it's an integral that means something. All right, so now we say this is an integral that's finding volume. Well, let's find volume in a different way. So, what's a different way for us to find our volume here? Washer method. Yes. So now, currently, if you look at our picture, the shell method, because of the dx, we're taking vertical slices. So, washer method says we're going to slice horizontally. All right. Well, good. Let's talk about these curves. The original curve, this is y equals arctangent of x. If I write this as x equals a function of y, what does it become? Tangent of y. All right. Now, this one, when I plug 1 into arctangent, what comes out? So in other words, what's the y value here? Pi over 4. Yeah, arctangent of 1 is pi over 4. So, here we go. We know we need the washer method, so we are going to integrate, and our washer method, a to b pi and outer squared minus inner squared thickness. That's our little formula. Okay, so where do we go? Well, our thickness will be what? When we're doing dy. Okay, so we have a dy in the end, which means it's a y integral. So where does y go from? 0 up to pi over 4. There's a pi. Now, the outer radius, so that says go from here to the very outermost part. How far out is that? It's 1. Then we're going to square that. Then we're going to subtract the inner radius. Well, how far away is the inner radius? Tangent of y squared. All right, so there we go. So we can say our original integral, we can interpret it. It's a volume. And we have another way to compute volume, and therefore we'll just do it our other way. Now, x arctangent of x, maybe that's not so easy. It's not impossible. Again, integration by parts. Can we integrate 1 minus tangent squared y? And how do we do it? Yeah, so first off, we use our trig knowledge, because we love trig. All right, Tangent squared, what do you replace that by? So what's the rule? So tangent squared by itself is secant squared minus 1. So you just have to be a little bit careful here. So notice that these ones don't cancel because of that minus goes through. So this is the same as the integral from 0 up to pi over 4 of pi times 2 minus secant squared y. And now we're in business. Integral of 2 with respect to y? 2y. Integral of secant squared y with respect to y? Tangent of y. And you evaluate from 0 to pi over 4. Well, 2 times pi over 4 will give us pi over 2. Tangent of pi over 4, 1. Plug in 0. 2 times 0, 0. Tangent of 0, 0. And that's the answer. So by reinterpreting, or rather saying, look, this integral means something, and I can do that same something in a different way, we can take an integral and do it without doing any integration by parts. There's no integration by parts. We didn't have to. Ah, cool. All right. Let's try another one. We have enough time. Plenty of time. All right. Find the integral 0 to 1 of x minus the pith root of 1 minus x to the pi quantity squared dx. Now, if you're wondering, is that a typo? Did you really mean to write the pith root? And the answer is yes. I really did mean to write the pith root. Okay. It's not a square root. Another way to write that, by the way, if you don't like that notation, you can write that last piece as 1 minus x to the pi raised to the power of 1 over pi. All right. And good news, I actually sketched it. So now we know we're looking for the area that's underneath this curve. So this is the x minus the pi through 1 minus x to the pi quantity squared right there. Okay, cool. Now, your initial reaction is, this has nothing to do with today. Good reaction. It feels like it has nothing to do with today. All right. That's fair. That's fair. But I think we should still try. It's good to try things. Now, how would you start with this integral? Is there anything we can do? Well, there's a 2 right there, right? Which means that we're squaring it. Let's do algebra. Yes, algebra. Our good friend. We don't get to see enough of you. So I can square this. So that'll become x squared. And then I'm going to get a minus 2x times the pith root of 1 minus x to the pi. Cross terms. And then plus, well, it has 1 minus x to the pi to the power 2 over pi dx. Let's talk about this middle term for a second. What does it feel like when you see that middle term? Do you see? Is it like anything we've done recently? What if we were to put a pi there? Then what would it look like? It'd look a lot like a shell method, right? A 2 pi, there's an x, and there's this curve. So it's like, hey, wait a second. It's all like the shell method. Let's think about this. So I have this curve, the pith root of 1 minus x to pi, which, by the way, in case you're wondering what this thing was over here, this is the curve y equals the pith root of 1 minus x to the pi. This is what it would look like. So we can think of this is almost a shell. In fact, it is shell if you take a 1 over pi. So it's 1 over pi times what? Well, it would be a volume where we spin around which axis? It would be a volume when we spin around this way. Okay? So that says, use your little shell method, you spin it, and you get a volume. Now, that's great. How does it help us? Well, you know what? I see this one on the end. Say, hey, how can I think of this integral? Again, if it helps, toss a pi in. What does it look like? This integral is almost a washer. And the only thing that's off is the pi. So really it's 1 over pi. So it is a 1 over pi times a volume. But volume of what? Well, when we spin this way. Right? Because that's what we're going to get. So volume around the x-axis. Now, look at these two volumes. What should be true? They're actually going to be the same. The reason is this curve is beautifully symmetric. It has symmetry. Now, it's not so obvious from the way it's currently written. So let me just note that you could write this as this formula, y equals the pith root of 1 minus x to the pi. If you raise both sides to the pith power, so y to the pi equals 1 minus x to the pi, or x to the pi plus y to the pi equals 1. So if you swap the role of y and x, it's still the same curve. Which says that these two are equal to each other. Now, normally, that may not help us a lot, but what else do we see? There's a minus. So what happens to these two things? They cancel out. We have no idea what this value is. You can't compute it. We don't care because it's canceling. So, by interpreting those pieces as volumes, what are we left with? Well, integral 0 to 1 of x squared. And I claim that integral we can do. What's that integral? 1/3 x cubed from 0 to 1, giving us the final answer of 1/3. That's it. So it's good to be able to detect, hey, I can think of this as a volume, and I can use that information to help me. All right. Well, let's try one more. Rotate the region in the first quadrant bounded by y equals square root of x. So y equals square root of x. That would be something that looks like this. Y equals square root of x. And then we have y equals 2 times the square root of x minus 3. Well, that's kind of interesting. So square root of x minus 3 says I don't even start existing until 3 because of that x minus 3. The smallest x value I can plug in here to get something that makes sense is x equals 3. But then I grow faster. So I'm going to look something like this. So it's sort of like a shark fin swimming through the water, coming to ruin our grade. But no problem. We're gonna figure this out. All right. Bum, 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 bum. All right. So what are we doing with this? Oh yeah, we're spinning this around a line. Y equals 2. Well, where's that line? Well, that turns out that where do they intersect? if you plug in x equals 4, you get square root of 4, which is 2. Here you get 2 times square root of 1. So it says you spin it around this line. So here's the line y equals 2. Okay, now we could do this either way. We could do this by washer, or we could do it by shell. I want to do it by washer, and I want to justify why. Not just because, I want to do it by shell. Not just because we learned shell, but if we were to do it by washer, we'd have to have one type of slice here, because the bottom is 0 and the top is there, and a different kind of slice here. Which means if you did it by the washer method, you'd have to do 2 integrals, which sounds like twice as much work. Our goal is to do just the right amount of work and then no more. So what do? So we're going to take a small slice this way, spin it around this line, and here we go. So we should be pretty adept at doing this. So we have 2 pi, our integral with respect to y. What will be, what's next? It's the radius, right? What's the radius in this picture? So you should think of this as y, and we're spinning around 2. So the radius is from where your slice is to where you're spinning. How far is that? 2 minus y. So this is our radius. We should set our bounds. Where does y go from? 0 up to 2. Yeah. So be careful, by the way. If you get to the end of it and you see that your answer is negative because you put in y minus 2, don't just be like, ha, 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 I'll just put a positive. We catch those mistakes. No. Get the sign. Signs matter. Now, what's the last thing we have to figure out? Height. Now, in this case, height is this length here. So we have the 2 curves. Y equals square root of x becomes x equals y squared. Just square both sides. Here, well, it's a little bit more interesting. You divide both sides by 2. Y over 2 equals the square root of x minus 3. Square both sides. Y squared over 4 equals x minus 3. So this is the curve x equals 3 plus, all right, as 1/4 y squared. So what's the height? How do you find it? You subtract right minus left. High value minus low value. See? High minus low, 2 minus y. High minus low. So it'll be 3 plus 1/4 y squared, subtract y squared. And then you do some work and you get an answer, but we will stop here because that's it for today. It's just algebra and integration from here. Have a good day. We'll see you next time.